Okay, hi. So let's continue from chapter 8. Now to subtopic 8.3, rotational dynamics. Okay, before I begin the term moment of inertia, okay, I hope that you can remember in our previous video. Okay, in our previous video, we state that the torque is analogous to the force, but now we are studying the moment of inertia. So the moment of inertia is analogous. What does analogous means? Analogous means that it's similar to the mass. Okay, so torque is analogous to the force, whereas the moment of inertia I is analogous to the mass. Okay, so what is the definition of moment of inertia? So moment of inertia represents an object resistance. Okay, resistance to the change in rotational motion. So if an object is harder to change its rotational motion, so if an object is harder to rotate, means that the moment of inertia is high. If an object is easy to rotate, means that the moment of inertia is low. Okay, so here, okay, it depends on the mass, the distribution of the mass, and the rotational axis chosen. So for example, let us see example A. Okay, this is easy to rotate. Why is this easy to rotate? Because you have a mass here, okay, and then the distance from the hand towards the mass is very short. Okay, it's very low. Okay, let me just state that the moment of inertia I, okay, is the summation of m, the mass, and the radius. So if the radius is small, means that the moment of inertia is low. Okay, so if the radius is small, the moment, assuming that the mass is constant, so the radius is small, the moment of inertia is low, so it's easier to rotate. Okay, so this is difficult to rotate because again I equals to m r here. There's a submission here. Okay, so you see that the distance between the mass and the forearm is so there's a large distance between the mass and the forearm, so we have large value of r, means that the I is increasing. So when it's increases in I, increases in moment of inertia, it's harder to rotate. Okay, so oh my god. Okay, so let me just state here, I'm sorry that if you can see, so it means that the mass is close to the axis, like what we said before, so it has smaller moment of inertia and it's easy to rotate. Okay, okay, again sorry for the wording here. So the mass is further from the axis, like I said, the r is longer, so it has a larger moment of inertia and it is harder to rotate. Okay, so let's see another example. Okay, so example here, in a playground, let's say there's 4 children in the playground. So this one, you can see that the distance of the children, okay, towards the center of an axis is high if you compare to this. So this one, okay, the distance of the mass is r is low. Okay, so the r value is low, whereas here the r value is high. So if the r value is high, means that it has large value of moment of inertia, therefore it is harder to rotate. Okay, hard, okay, h, hard. Whereas for this, okay, you have the value of r is small. Okay, so the moment of inertia I is small, so this is easy to rotate. Okay, because the moment of inertia, the tendency for the object to rotate, okay, is easier. Okay, so the large moment of inertia requires more torque, meaning that it requires more force to change the body's rotational speed. Okay, so from here I'm going to just show you the example for different, because we have different shape of an object. Okay, we have cylinder, we have disc, we have a rod, okay, and sphere. So all of those have different moment of inertia. Okay, because it depends again on the mass and the distribution of the mass and the axis of rotation. So you can see here, you have a thin cylindrical shell, the mass distribution must be different, and also the distance also must also vary, right? So you have here different values of moment of inertia. Okay, but sir, do we have to memorize all of this? Okay, you don't need to worry about that. Usually the question gives you the moment of inertia. Okay, usually it gives you the moment of inertia, so you don't have to know about how to derive or how to memorize this formula. Okay, Okay, a heads up. So the moment of inertia of a flywheel. Okay, so this statement is just saying that you should prepare for your experiment, because in experiment 4 you will try to find the moment of inertia of a flywheel. Okay, so this experiment can be very fun, and if you're inside my class, it should be fun lah. Okay, now, okay, let's see the relationship between torque and angular acceleration. Again, torque is analogous to the force, and acceleration is angular acceleration is analogous to the acceleration, right? So actually we are discussing now again on chapter 4, okay, the Newton's second law of motion, but it specifically is for the rotational motion. Okay, so let's consider our diagram here. Okay, you can see that there's so many forces. There's force 1, 2, 3, up until around 5 forces lah. Okay, but again, we have a pivot point, okay, point of rotation at the center. Okay, so there will be a torque. So F1 corresponding to torque 1, torque 2, torque 3, up until the total number of torque. So you can have what you call a net torque, the total torque, okay, based on the total number of horses, okay, which is the summation lah of all the torques, right? So here is again stating the Newton's second law for rotational motion. Okay, what is the Newton's second law for rotational motion? It means that a rigid object that experiences a net torque, okay, means that it is not what we discussed in our previous video, which is the equilibrium. Now we are having a net torque, okay, because there's so many forces involved inside this diagram, so there should be a net torque, okay, and the net torque here is not equal to 0, because now this net torque will cause the object to rotate more fast. When it rotates more, it means that it causes an angular acceleration. So that's why the torque here, the net torque, is equals to I alpha. Okay, so if you can see, if you can relate it back, okay, it is almost analogous to, again, F equals to M A. Okay, again, it's just a repeat of what you did in chapter 4, but instead of linearly, we're focusing now on rotationally. Okay, so the mark here, net torque causes angular acceleration, is just a repeat of what I said from before. Okay, so here we're going to analyze the relationship of torque with the relationship of force. So from our previous slide, we have torque equals to I alpha, right? So let's try to rearrange so that we can study this equation more clearly. So if you rearrange alpha as a subject, okay, you have alpha means that you put the moment of inertia below, so you have alpha equals to net torque over I. Okay, what can you get from this formula? You can get that the angular acceleration here, okay, is directly proportional to the net torque. Okay, is it true? Okay, so from our previous statement, I state that if you have a net torque, it will cause the object to rotate even faster, which is actually, this statement is actually true. If you have a net torque, meaning you have a net torque means that you have many amount of forces, okay, it will cause your object to rotate more. Okay, so let's see our next relation. Okay, the angular acceleration is inversely proportional to the moment of inertia. Okay, it's inversely proportional. So what it means is that, again, moment inertia is the object's resistance to rotation, right? So if you have a large moment of inertia, means that if the object is harder to rotate, then of course lah, your angular acceleration is going to be very low, right? Okay, so it has an inverse relation. So so I hope that you get that. Okay, if the object is harder to rotate, of course lah, it's quite harder to accelerate the object. Okay, and of course there are going to be some problem solving strategies, okay, involving this rotational dynamics. Okay, so again, I won't explain it in too much detail because you're going to be explaining this in more detail inside your tutorial class. This is just a ways, many steps on how you solve the rotational dynamics question. First, by all means always draw a clear and complete diagram, okay? Because usually you're going to have like a pulley and a mass on a pulley system, okay? That's the standard question that will always be asked, okay? Then you need to choose an object. Like I said, a mass and a pulley, you can choose either the mass or the pulley, so you need to choose those objects so that the system will be steady. So if you choose the pulleys, for example, if this is a pulley, you need to know how to do the rotational kinematics on that. If you choose like the mass, then you need to know the usual F equals to ME. Then because we're dealing with forces, you need to draw the free body diagram. So for example, it might have, let's say, okay, an object, okay, like here, okay, so you have weight there. Then probably have, let's say if there's a rope, you have tension there. Okay, tension, okay. So okay, so you need to identify the forces and draw the free body diagram of the forces. Okay, next you need to know the axis of rotation, meaning that you need to know the pivot point, okay, and you need to determine the torque. Okay, so which forces which moves, okay, the closest distance through the pivot point, okay, and you need to assign the correct sign, meaning that if it's clockwise, it's a negative torque, but if it's an anti-clockwise, it's a positive torque. Then you need to apply torque net equals to I alpha. Okay, so here you can solve a question which involves find the angular acceleration. Okay, and then you apply F summation of F equals to ME, okay, and other laws or principle as needed. Okay, this is, you need to focus here, as needed. What it means here is sometimes the question sometimes the question is really simple. Find the moment of inertia, find the mass, or find the angular acceleration. So you don't need to apply number 6. But if the question states find the acceleration A, then you need to combine the rotational kinematics and the linear kinematics together to find the acceleration value, or find the tension, or find the external forces, for example. So sometimes you need to combine the rotational kinematics and the linear kinematics. And again, number 7, solve the resulting equation. So I can't show you an example of a question. Okay, the example will be shown inside your tutorial classes, but I hope that this video helps you. So we will go to our final subtopic in the next video, which is conservation of angular momentum. Right, I hope you enjoy. Bye.